The National Electrical Code, specifically Section 310.15b2, addresses ampacity correction factors for conductors in cable trays. The primary concern with bundled or stacked cables is heat dissipation. When multiple current-carrying conductors are grouped together, the heat generated by each conductor can raise the overall temperature, potentially exceeding the insulation's rating. This can lead to premature failure of the insulation and increase the risk of electrical hazards. Therefore, the NEC provides guidelines to derate the ampacity of conductors based on the number of current-carrying conductors in a raceway, cable, or bundle. The issue at hand revolves around how these derating rules apply when using cable stackers, particularly those that arrange cables vertically. The core principle is that adequate spacing between cables allows for better heat dissipation. When cables are tightly packed, heat is trapped, increasing the conductor temperature. If cables are spaced apart even slightly, the air circulation helps to dissipate the heat, reducing the temperature rise. The interpretation of Section 310.15b2 becomes critical in this scenario. If the cable stacker maintains sufficient spacing between the cables to allow for adequate heat dissipation, then derating might not be necessary. However, if the cable stacker packs the cables tightly together, effectively creating a bundle, then derating would be required. The NEC does not explicitly define sufficient spacing in this context, leaving room for interpretation by electrical inspectors and engineers. Several factors influence the need for derating when using cable stackers. Firstly, the ambient temperature of the environment plays a crucial role. In hotter climates, the heat generated by the conductors is more difficult to dissipate, increasing the likelihood of needing derating. Secondly, the type of insulation used on the conductors affects their ability to withstand heat. Higher temperature-rated insulations, such as those rated for 90 degrees Celsius, can tolerate higher temperatures before derating becomes necessary. Thirdly, the load on the conductors also impacts the amount of heat generated. Conductors carrying near their maximum ampacity will generate more heat than those carrying a smaller load. The specific design of the cable stacker is also an important consideration. Stackers that use a design that promotes airflow around the cables will reduce the need for derating. For example, a stacker with open sides or built-in air gaps will allow for better heat dissipation than a stacker that completely encloses the cables. The NEC provides ampacity tables that list the allowable ampacities for various conductor sizes and insulation types. These tables are based on specific conditions, such as an ambient temperature of 30 degrees Celsius and no more than 3 current-carrying conductors in a raceway or cable. When these conditions are not met, the ampacity must be adjusted using correction factors. The correction factors for ambient temperature are found in NEC Table 310.15. These factors reduce the allowable ampacity of the conductor when the ambient temperature exceeds 30 degrees Celsius. The correction factors for the number of current-carrying conductors are found in NEC Table 310.15b3. These factors reduce the allowable ampacity of the conductor when there are more than 3 current-carrying conductors in a raceway, cable, or bundle. In the case of cable stackers, the number of current-carrying conductors in the stacker must be considered when applying these correction factors. If the stacker contains 4 or more current-carrying conductors, the ampacity must be derated according to Table 310.15b3. The NEC provides examples of how to apply these correction factors in Annex B. These examples can be helpful in understanding how to calculate the correct ampacity for conductors in various situations. One key aspect to consider is what happens after the cables leave the stacker. If the cables separate and are no longer bundled together, the derating requirements may no longer apply. The reasoning is that once the cables are separated, they can dissipate heat more effectively, and the temperature rise is no longer a concern. However, if the cables remain bundled together after leaving the stacker, the derating requirements would still apply. This highlights the importance of considering the entire cable run when determining the need for derating. The inspector's role is to evaluate the specific installation and determine whether the cable stacker creates a condition that requires derating. This involves considering the ambient temperature, the type of insulation, the load on the conductors, the design of the cable stacker, and the cable routing after the stacker. In situations where there is doubt, it is always best to err on the side of caution and derate the conductors. This will help to ensure that the installation is safe and that the conductors will not be overloaded. It is also important to document the derating calculations and the rationale behind them. This will provide a record of the decision-making process and can be helpful in the event of a future inspection or problem. To further clarify the application of NEC 310.15 B2 in the context of cable stackers, let's delve into specific scenarios and interpretations. Firstly, consider a scenario where a cable stacker is used in a well-ventilated area with a relatively low ambient temperature. In this case, the heat generated by the conductors may be easily dissipated, and derating may not be necessary. However, it is still important to consider the other factors mentioned above, such as the type of insulation and the load on the conductors. Secondly, consider a scenario where a cable stacker is used in a confined space with a high ambient temperature. In this case, the heat generated by the conductors will be more difficult to dissipate, and derating will likely be required. The amount of derating will depend on the specific conditions, but it could be significant. Thirdly, consider a scenario where a cable stacker is used to support cables that are carrying different types of loads. For example, some cables may be carrying lighting circuits, while others may be carrying motor circuits. In this case, it is important to consider the load on each individual cable when determining the need for derating. Cables carrying heavy loads will generate more heat and may require more derating than cables carrying lighter loads. Fourthly, consider a scenario where the cable stacker is used in a corrosive environment. In this case, it is important to choose a cable stacker that is made of a corrosion-resistant material. This will help to prevent the stacker from deteriorating over time, which could compromise the safety of the installation. The NEC also addresses the issue of cable trays, which are similar to cable stackers in that they are used to support and route cables. NEC Article 392 provides specific requirements for cable trays, including requirements for derating conductors in cable trays. These requirements are similar to the requirements in NEC 310.15 B2, but they are more specific to cable tray installations. It is important to consult Article 392 when designing and installing cable tray systems. One common question that arises is whether cable stackers are considered to be cable trays. The answer to this question depends on the specific design of the cable stacker. If the cable stacker meets the definition of a cable tray in Article 392, then it would be considered a cable tray and would be subject to the requirements of the article. However, if the cable stacker does not meet the definition of a cable tray, then it would not be considered a cable tray, and the requirements of Article 392 would not apply. The definition of a cable tray in Article 392 is a unit or assembly of units or sections and associated fittings forming a structural system used to securely fasten or support cables and raceways. This definition is fairly broad, and it could potentially include some types of cable stackers. Ultimately, the determination of whether a cable stacker is considered a cable tray is up to the electrical inspector. The inspector will consider the design of the cable stacker and whether it meets the definition in Article 392. Another important consideration is the listing and labeling of the cable stacker. If the cable stacker is listed and labeled as a cable tray, then it is likely that it would be considered a cable tray by the inspector. However, if the cable stacker is not listed and labeled as a cable tray, then the inspector may be less likely to consider it a cable tray. The listing and labeling of electrical equipment is an important aspect of electrical safety. Listed and labeled equipment has been tested by a recognized testing laboratory and has been found to meet certain safety standards. This gives the inspector confidence that the equipment is safe to use and that it will perform as intended. In addition to the NEC, there may be other codes and standards that apply to cable stacker installations. For example, some local jurisdictions may have their own electrical codes that are more stringent than the NEC. It is important to consult with the local authorities to determine which codes and standards apply to a specific installation. Furthermore, manufacturers of cable stackers often provide installation instructions and guidelines. These instructions should be followed carefully to ensure that the cable stacker is installed correctly and safely. The manufacturer's instructions may also provide information on the allowable ampacity of conductors in the cable stacker. In summary, the application of NEC 310.15 to cable stackers requires a careful consideration of several factors, including the ambient temperature, the type of insulation, the load on the conductors, the design of the cable stacker, and the cable routing after the stacker. The electrical inspector has the ultimate responsibility for determining whether derating is required in a specific installation. In situations where there is doubt, it is always best to err on the side of caution and derate the conductors. It is also important to document the derating calculations and the rationale behind them. By following these guidelines, you can help to ensure that cable stacker installations are safe and compliant with the NEC. The use of cable stackers can be a convenient and efficient way to manage cables, but it is important to do so in a way that does not compromise electrical safety. Proper planning, installation, and inspection are essential to ensure that cable stacker installations are safe and reliable. Remember to always consult the latest edition of the NEC and any applicable local codes and standards before designing or installing any electrical system. Continuing education and training are also important for staying up to date on the latest changes in the electrical industry. This information is for educational purposes only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or inspector before making any decisions about electrical installations.